All right, everyone. Hello. Today is our class number 16, I believe. We are going to do the SVM in Python. So for today, the plan is to go over the SVM classification. We'll be working with the Washington, D.C. bike share dataset. This is the dataset that you're familiar with already. We have worked on this dataset for your homework 7, then we did the KNN. At the end of the day today, I'm going to compare the output of the SVM classifier versus the KNN classifier. And not surprisingly, we will see that SVM is going to do a lot better job because that it's high dimensional data. KNN was not designed for those kind of data sets. The data set is large, relatively, in econometric kind of word is large. 17,000 observation in machine learning language is tiny. But still, compared to the other data sets that we work with in the class, is relatively large, 17,000 observation, and the dimension is also, when we make everything into dummy variables, the dimension is also large. So it's not surprising at all that the SVM should and will outperform the KNN. Okay, so let me quickly remind you of the variables in the data set. I think I have it open here. Yeah, so this Washington, D.C. bike share data. And so the data is, as I said, 17,000 observations from collected in 2 years, so 11 and 12, 2011 and 12. And basically, the name of the variables are, so what do we have? We have seasons, definitely it should be changed into a dummy variable. We have spring, summer, fall, winter. Year, as I said, 2 years. Again, we have to make this one dummy variable as well because we want to control for the effect of year 2011 versus 2012. Month, January to December. Again, this must be dummy variable. Hours, 0 to 23 must be changed to dummy variable. Holiday, whether day is holiday or not. Again, this must be a dummy variable. Weekday, day of the week, counting from 0 is Sunday, and then the 1 is Monday, and etc. Again, this must be dummy variable. So as you can see, we have lots of categorical variables already, right? So there's, again, it's not surprising that the SVM should do a better job compared to KNN. Not biz day is if the day of the week is a holiday or not. If it is holiday, it's 1, otherwise 0. Weather situation, it goes from good to bad, right? So 1 is clear, and then 4 is heavy rain, so it's a severe condition. Temperature, so temperature, weather also should be dummy variable. Temperature, humidity, wind speed, these are continuous variables. We don't need to do anything about them. But in this data set, they're already coming as a standardized version. So they're already standardized. And we're going to erase this variable because we don't need to keep track of every single day. This is the date. And count, finally, is the count of total rental bikes. So this is a classification model. So this means that we are going to say, we are going to define a new variable called overload, and we say if the system is going to be overloaded if the number of orders is above 500, the count of bike orders above 500. So if it is above 500, we call it 1. If it is below 500, we call it 0. And the name of the target variable is going to be overload. Okay, so that was the data set, and yeah, let's go ahead and start the SVM. And I'm going to have this contextual help open here because we will go over the different features of the different inputs of the SVC function in Python. Okay, so as usual, let's run the packages. Random state is equal to 1000. Even if you put the random state is equal to 1000, when we get to grid search, well, let me talk about it later because it doesn't guarantee that your output is going to be exactly the same as mine. So that's my point, but I'll explain why. Okay, let's read the data set and load it as df. So this is our data set. So look, if you look at the head of the data set, so these are the variables that we just covered, right? So we have to go ahead and transform this one and into overload if it is greater than 500, 1, less than 500, 0. And then we have to make sure that all of these things are dummy variables. So for example, weekdays, we have to have 6 dummy variables, erasing the first one, deleting the first one. And as you can see, the continuous variables are already standardized. So this is important. Next class, I'll talk about feature scaling. And it is important that sometimes, in order to avoid the data leakage from test set to train set, it is better to only fit the standardization using train set and then use transform to the test set in order to make sure that we are not leaking data from test set to train set. But here, because the data is already coming as a standardized version, and we know that there is no outlier, it really doesn't matter. I'm going to go ahead and standardize the entire data, okay, in one line. But I'll be specific next class. That's what I mean to avoid data leakage from test set to train set. All right, so this data set is super clean, but it doesn't hurt to double check. So there's no NA here. We can look at the information. All of them are integers or continuous random variables here. We know that we have to change lots of them to dummy variables. So let's go ahead and do that. But before that, let's construct our target variable. We're going to name it as overload, and it's defined as we're going to use where function from NumPy. This is a very useful function. It works like if else in R, for those of you who are familiar with R. So this is pretty much the same, does the same job as if else do in R. So basically it says that if some condition is true, then this, otherwise this. So we say if some condition is true, if count is greater than 500, assign 1, otherwise 0, and then save it as overload, right? Then it is always good to, when you're doing classification, look if your data set is balanced or not, right? So you can use cross table. So I'm going to use cross table overload versus overload, basically, and then make sure that we are normalizing everything multiplied by 100. So this gives me the percentage, right? So this data set is relatively imbalanced. Again, if it is 1, 2, 3%, I call it imbalanced. If it is between 2, 3 to 10%, I call it relatively imbalanced. Anything greater than 15 to 20%, I call it relatively balanced. And then 50, 50, 40, 60, these are, in my opinion, they're very, very balanced, right? I think for your next homework, you'll see it's 35 versus 65. So you should call it relatively balanced. So because I get this question a lot from students, what is relatively balanced? What is relatively imbalanced? So that's one more time. So again, if it is 7%, 10%, 12%, I call it relatively imbalanced. All right. Now, let's quickly add this overload to the data frame. So I'm going to add this variable that we just constructed to the data frame. We call it overload. And get rid of the count, look at the columns. Oops, because I already deleted this one. So it really doesn't matter. I already deleted it. It's not going to change anything. Then we need to change the type of the categorical variables, right? Remember season, year, month, hour, holiday, weekday, and not business day, and weather situation. They are all should be categorical variables. Now we transfer them into categories. Down the road, we're going to make them dummy variable. But before that, let's look at the pair plot. And for the continuous random variables, right? Because let me actually ask you a question. Why do I need to look at the pair plot if he was the target variable? So we talked about this one previously, but why do you think that it's a good idea to look at the pair plot before running the model? You're doing classification. In regression, we don't care that much because maybe you're not doing linear regression for different regression models. Basically, if you look at the correlogram, that's enough. But for classification, it's a good idea to look at the pair plot for continuous random variables. So why do you think that's the case? Any idea? Remember, we said that we are interested in the colors are the target variable, right? We're interested in the distribution of the continuous random variable. If the continuous random variable, if the distribution for different colors are separated from each other, this is a very good sign. It means that you're going to end up with a good classifier based on the continuous random variables, right? And here, well, to me, it's not that bad. The average is completely different, right? When I look at the distribution. So it's a sign to me that at the end of the day, I should get a good classifier based on the continuous random variables, right? But if I add the dummy variables for, I think, lots of dummy variables for the categorical variables, then maybe KNN is not going to do a good job. But the hope is that SVM is going to do a good job today, okay? So there's this trick that we haven't talked about it in Python crash course. There's this method called difference. And so in R, when you want to exclude some column from the data frame, you simply do a minus behind the name of the variable, right? In Python, it doesn't work like that. So in Python, if you want to do the same thing, you have to use a method called difference. So basically, it says that if I simply run df columns, what do I get? I get the name of the columns, right? These are the name of the columns. I want to plot the pair plots not for all the variables. I want to exclude the categorical variables. So when I say dot difference and then put the name of this is a list, right? List of the variables that you want to exclude. Then it's going to give me the columns from the data frame excluding the whatever is here. This is a list of categorical variables, right? So you'll see it's going to end up with, well, didn't I drop this one? No. So it's going to end up with humidity, overload, temperature, wind speed, and etc. So these are continuous random variables. I could have actually get rid of the overload as well. So that's why I see this blank distribution here. Does that make sense? Okay, so this is a very useful technique. Just be aware that you can do that, because usually sometimes you have hundreds of variables in the right hand side and you want to exclude some of them or a subset of them. You don't want to write them manually. So the difference method is useful. All right. So by looking at this pair plot, it's again, I expect to get a good output out of this SVM. So it's not always guaranteed, but it will give you I don't know, some benchmark. Okay, now let's go ahead and scale the features. For this exercise, I'm going to go ahead and scale the entire data set using a standardization, right? So basically, and we know how the standardization works, right? You take the average out, divided by standard deviation, and everything is going to be transferred to normal standard distribution, right? And so for this class, I want you to take it from me, as given. So we are going to transfer everything to using standardization. But next class, I'll talk more about feature scaling. So why we did not, for example, min max scale, or why we did not different normalization, right? So again, for this class, let's standardize everything. And then next class, I will explain why this method should work better compared to normalization when I look at this data set, right? All right, so I'm going to use getDummy function to make sure that all the categorical variables that I already defined are the dummy variables now. When I look at the name of the columns, actually, we can see what's the size of it, right? If I do shape, so we have 53 features, right? And 53 is relatively high dimension. So that's why our KNN was not, well, we cannot compare yet, but exposed, so you will see that the KNN was performing a lot worse than the SVM, because SVM is powerful when it gets to high dimensions when using those kernel functions, right? Kernel trick. All right. Then, so we can quickly look at the head of the data set. I'm going to go ahead and transform all of these dummy variables into, I will standardize all of them. So let's do that. So I'm going to import the standard scaler from scikit-learn pre-processing. And I'm going to do it in one step. So what I mean by one step, I say that, OK, define an object. This is my scalar. Let's call it scale or scalar. I'm going to transform the entire data set, right, using this standardization. And the output is going to be an NumPy array. And then I'm going to transfer that one into a data frame, because if you want to work with data frame, we need the name of the columns and etc. And at the end of the day, I'm going to replace the overload, the new overload with the old one, because my target variable should not be standardized, right? So the target variable should be 0, 1. I could have done the same thing, exactly the same thing by here. If instead of df, I say df drop, and then add the overload, and then get rid of this line, right? So basically, both of these things are going to do the same job. Okay, so just be aware that we are transforming the entire data set and then make the target variable again back to 0, 1. In this exercise, it really doesn't matter, but we will see next class that when that's the case, that you want to make sure that you fit the transformation using this train set, and then use that, for example, average or standard deviation that you calculated, and apply it to test set. So to avoid the leakage between test set and train set. In this case, because the data originally came as a standardized version and I checked that there's no outliers, I'm not worried about that, right? But I'll talk about it more. So there's one more step if you want to do it separately. So here we transform the entire data set in one step. Okay, now if I look at I call the new data frame as DFSC scaled. So this is, at the end of the day, this is a data set which is ready for our machine learning algorithm, right? And as you can see, all the variables except the overload are standardized. It means that we take the average out and divide it by standard deviation. And not surprisingly, many of these things are the same because these are 0 ones, right? So here in this case, 0 is minus point, transformed to minus 5.9, and 1, I don't know, plus something. It's not symmetric, right? Yes.
I feel like you should standardize it before you do the dummy variables.
You say the standardized, but do not touch the dummy variables?
Yeah.
Well, we'll talk about it next class.
Okay.
We will talk about, this is also one alternative. And it seems that for this data set, this was the best one, okay? There are 6 different methods that you could transform this data, and I'll talk about it next class. But for now, let's assume that the standardization is doing the best job, and I want to compare apple to apple, so that's why I want to do standardization. Okay, but good question. Okay, now, so this is our new stuff, right? We're gonna from scikit-learn, we're gonna import from scikit-learn.svm class, we're gonna import SVC, support vector classifier, and I agree, this is not necessarily a good name because we know that SVC is something that we don't have kernel trick from the lecture. But here in Python, when we say SVC, we're talking about SVM classification. Does that make sense? And when we say SVR, we're talking about SVM regression. So, but still, I think maybe if you use SVM underscore classifier, that was a better name. But anyways, because we know that there's a difference between MMC, SVC, and SVM. So this here means SVM classification, okay, because we are applying the kernel trick. All right, so let's look at what's inside this SVC, talk about the inputs, and then we are ready to train the model. Okay, remember what are the hyperparameters that you're interested in. So from the lecture notes, we know that there's this C, cost of misclassification. The larger the cost, the narrower the margin, right? So if the margin is narrowed, bias is higher or smaller, lower or higher. If the cost is large, cost of misclassification is large. So the margin is narrower. When the margin is narrower, bias is higher or low. When the margin is narrower.
When the margin is narrower.
Bias is lower, right?
Yeah.
And you have to practice this multiple times, right? The bias is lower. And again, this is going to control the trade-off between bias variance, right? So if we increase the margin, then the bias is going to be high, the variance is going to be small, right? Okay. Then, so C is something that we're interested in. Kernel is something that we're interested in, and we know that different options for kernel are, well, the most common ones are the 4 ones, right? Linear, RBF, polynomial, and sigmoid. And gamma, if you're using RBF kernel, which we know that it's going to, usually it's going to outperform all of the other kernels. So gamma is usually based, some part of them are hyperparameters. And that controls how far that Gaussian multivariate distribution is reaching out, right? So if gamma is small, it means that the variance is large, so it's reaching out to further points. If gamma is large, it means that the sigma is small and it's basically reaching out more locally. Okay, so just keep in mind these 3 variables, and then when we go to Python, let's look into them. So by default, C is equal to 1. So if you do not pass anything, and usually we should start with the basic classify SVC without changing the inputs. Then down the road, we're going to use GridSearch to update the hyperparameters, right? So the C is equal to 1. Kernel by default is RBF. Degree, if it's 3. This is if you're using sigmoid function, sigmoid kernel. And gamma, by default, it's a scale. Scale means that it's 1 divided by its, I think, number of observations, or the other way around. Let me look at the scale. Yeah, scale. Can I pass it? So this is gamma. Yeah, gamma is, yeah, if it is a scale, it says that 1 divided by n multiplied the variance of x. If it is auto, it's 1 divided by number of features, right? So it's inverse of, if you leave it as nothing, by default, it's going to be a scale. And it's inversely related to the variance of your x variable, right? Your feature. Then shrinkage coefficient, probability. So we know that the output of the SVM is not probabilities, right? These are 0, 1s, right? But there are methods out there that you can still transform them to probabilities, but I do not recommend it because it is estimation on top of estimation. So for example, you can use logistic regression to transform the SVM outputs into probabilities. But again, I personally do not trust those numbers because you're making another estimation on top of your original estimation. So it's going to, and if there's any bias in any of this, it's going to give you fake numbers, right? But I just want to let you know that there are ways that you can get probabilities out of SVM, okay? Actually, it's called, there are some models called RVM, relevance support, no, relevance vector machines, and that gives you the probabilities as well. But me personally, I don't trust the estimation over estimation because if it is biased, you're making it, I don't know, it's machine learning itself. Usually there are lots of noisy data out there. So if I want to do estimation, I'll try to do it. That would be best if I do it once, not estimation on top of estimation on top of estimation. But sometimes if you have to come up with probabilities, just be aware that this option is there, okay? Tolerance, cache size, class weight. Let's see, what else do we have? This one is also important. Decision function shape. I think I like the name that the Python is using, OVR. What do you think this stands for? Well, decision function shape, when we have multiple classes. We talked about OVA versus OVO, right? One versus one, one versus all. So I like the Python name better because it's one versus rest. And one versus rest to me is better name than one versus all because it's not one versus all. It's literally one versus rest. But the textbook is using one versus all. And I also use one versus all in my lectures. But I believe that this is a better name. So again, if you have multiple classes, you can do one versus rest or one versus one. By default, if you just leave it blank, you will get one versus rest. If you have binary classes, it really doesn't matter. So 0 versus 1, 1 minus 1. All right, and the random stage is random stage. So I think these are all the inputs from the SVC function that we should know. And the most important ones are C, kernel, and gamma. Okay. Now let's continue and try to train the model. So we're going to train the model using the train set. So fit the model, use train set. And depending on the memory on your computer and the size of the data set and the dimensionality of the data set, it may take some time. So now let's make some predictions on the test set. So these are pretty standard steps, right? So you fit the model using train set, you make prediction using the test set. What are the outputs here? These are going to be 0, 1s, right? Because by default, the output of the SVM is going to be 0, 1. Now I'm going to make a new data frame, call it predictions, and just look at y, actual y versus predicted y. We call it y hat side by side, right? I look at the tail of it. So let's see why it's not working. Okay, I may have skipped a couple of lines out there, so let me make sure that I can go over all of them. Because when I dropped one of the variables, I believe that it changed the shape of the. Okay. And complain. All right, so these are the predictions. And as you can see, so for example, this is a correct classification, this is correct, but this is incorrect, right? So the actual is 1, but prediction is 0. And this was our very basic model. We didn't do any kind of optimization yet, tuning hyperparameters. Just keep in mind that this was a basic output. All right, Like other classifiers that we did in the class, logistic regression, KNN, we are going to make our own SVM report. You can use the standard outputs, the standard functions from scikit-learn package, or you can use the function. You can borrow my function. I call it my SVM report. But basically, what I do here is that we have seen this before. So we just make sure that what are the inputs that we wanted to have in our function. So okay, pass me the train set, test set, and I want to make sure that I can play around with C, gamma, and kernel. And the default values, I'm going to use the default values of the Python, right? So C is equal to 1, gamma is equal to scale, and the kernel is equal to RBF. The rest of it is going to be exactly the same as the previous functions that we did in KNN and logistic regression. And here, I'm going to also report error rate like what we did in KNN because I want to make sure that we can compare them. You can add and remove any features from this customized function if you wish. Okay, then now, so it seems that the accuracy of the model is high, 97%. But should I trust this number? The answer is relatively, most probably no. Why? Because the data is relatively imbalanced. So which one is a better number to look into is the F1 score, right? So F1 score 78%. This is a decent number, right? So I know that the false negatives are high, and if you want to reduce the false negatives, if it was KNN, you could reduce the threshold or logistic regression. But in SVM, it is what it is, right? So you cannot play around with that threshold. Again, there is a method called RVM, but that's beyond the scope of this class. But if you're curious, you can look it up, relevance vector machines. All right. Then ROC and AUC. We cannot define ROC. Why? What was the definition of ROC? The plot, do you remember the plot? So what does ROC give us? How is it?
Classification?
Yeah, but ROC basically plots false positives, true positives for different thresholds, right? Here, it doesn't make any sense to have different thresholds, so we cannot do our ROC or AUC, right? Does that make sense? Is it clear? So in SVM, we cannot play around with that one number. We cannot report that one number AUC. I think regardless here, because the data in imbalance, I want to look into this one. If I want to optimize anything, I want to get a bit better F1 score. All right, now let's talk about grid search. So going back to the slide. So as a quick reminder, what is grid search cross-validation? We're going to pass the multiple options to our hyperparameters like kernel, C, gamma, and we can use fivefold cross-validation to basically going over a grid, repeat this fit and this training and testing model. I don't know, depending on how many values you're going to pick here, maybe hundreds of times, and then pick the best one, right? So this is what the grid search cross-validation is doing. So you can read through this these paragraphs on your own, but basically it's talking about what is grid search cross-validation, and these are, and I put some extra links for you if you want to go over them. So I have to define my, I call it my param grid, and this is a dictionary. I'm going to pass whatever value you want to play around with cost, gamma, and then kernel, right? So for cost, I'm going to say that go over 10, 100, and 1,000. You can because by default you can add 1 as well. So usually if you do 1, 10, 100, and a very large number is also good. So maybe instead of 1,000, you can do 10,000, right? But the reason that I keep it small, relatively, I have only 3 of them because I want to make sure that we can do this grid search in the class. And this also depends on the speed of your computer. So for the homework, I assume if you're using your own laptop, it's going to take a long time. So you can just restrict it, for example, to a couple of C's, couple of gammas, and then maybe only RBF. And so let me go ahead and define this my param grid. So what's going to do is going to look any combination of these. So I have 3 of them, and 1. So 3 by 3 is 9. Multiply 1 is 9. And if I do fivefold cross-validation, is 9 multiply 5. So 45 times it's going to repeat this process, right? you can imagine how quickly it's going to get out of control. If I have 5 of them here, 5 of them here, and 4 of them here, it's going to be a lot, right? 5, 5, 25, 400, and then if I have 10-fold cross-validation, it's going to be the 1,000, right? So it's going to take a lot of time. All right, so we're gonna do from model selection class, we're gonna import GridSearchCV, and it is case sensitive. Be careful that this G is capital, S is capital, and C is capital, CV is capital. And this is a function. It's called GridSearchCV. So let's look at the documentation for the function. Basically, you need to pass, it's very much the same as the cross-validation. You need to pass the estimator. So we're going to pass the basic, for example, SVC here without changing anything, right? So my estimator is going to be SVC by its default inputs. Then you need to pass param grid. So I'm going to I just gave it a name. I call it my param grid. So this is what I'm going to pass as a different combination of the parameters that you want to test. And this scoring, let's say number of objects, refit. So this is important. If I say refit is equal to true, basically what it does is at the end of the day, this grid search cross-validation is going to go ahead and find the optimized combination of the hyperparameters and refit the trained data set one more time for you and save it. Save the output so you can call what was the best estimator, what was the best hyperparameters, and then what are the predictions based on that model. Does that make sense? What does the refit do? Okay. So it's going to refit the entire train set using the optimized hyperparameters. This verbose this literally means verbose. So if I set it equal to 0, when I do the grid search cross-validation, if the verbose is 0, you'll see no documentation here, right? But if I say, for example, give me 1 level, give me 2 levels. So usually 2 levels is enough because basically if I do 2 levels, it's going to tell me that, okay, what was the first thing that's doing? So for example, we have 5-fold cross-validation. It's going to go over every single of these combinations 5 times, right? So C is equal to 10, gamma is equal to scale, kernel is equal to RBF, right? 10 scale RBF 5 times because it's 5-fold cross-validation. Then I have C is equal to 10, gamma is equal to 0.1%, and the kernel is RBF 5 times, right? So I'm going to have 45 of these combinations, right? Because why? Because again, 3 multiply 1 multiply 5-fold, it's 45. And so let me run these couple of lines and then run this one. This is going to take a little time. So as you can see, because the verbose was 2, I'm seeing what's going on behind the scene. If you do verbose is equal to 3, you will see even more information, right? But to me, usually I want to see how quickly it's done. So if you go ahead and do, for example, kernel is equal to linear is going to take a lot longer than RBF. And for some of these loops, it's going to take minutes, right? So my office computer is not super fast, but the memory is 32 gigabytes. It's not that bad. But still, you can see it's going to take a little time. So I think I have an HTML version saved for you and show you that it took me 12 hours for the regression one that we are going to do next class. But even I loaded on Google Colab, it wasn't fast. Even I was offered some GPU, but it was not that fast. So let's wait maybe a couple of more minutes until it's done, because it has to go over 45 different fits. And then the best fit, whatever it is, we can extract the information for the best fit and then refit the entire thing using that best fit, right? But what are the caveats of grid? So while it's doing the job, what are the caveats of grid search? How do I know that there's only these 3 or only these 3 or only RBF, right? So you have to have some prior information, right? Some prior belief, and then maybe test it out. Unless you have a super powerful computer, then you can say, okay, I don't have any prior beliefs. So let's go ahead and try every combination. But again, usually it's not that easy to come up with the best global, let's say, minimum. All right, are we done? I think so. And then, so if I said, guys, remember, I saved it as grid. You can call it anything, right? You can call it my grid, and then you can extract information from that grid. So if I go ahead and say grid.tab, see, these are everything that I can extract from that grid search cross-validation, right? I can look at the best index, best parameters, best score basically best R score out of those 45 fits, right? Classes, cross-validation result, decision function, error score, estimator, and etc., right? So the ones that we're interested in is, first of all, tell me what was the best combination. So if you just do grid.best parameters, it seems that out of this combination that you pass to the grid search cross-validation, it seems that out of those 9 options, if C is equal to 1000, gamma is equal to 0001, 1 over thousands, and then kernel is RBF, this is the best combination, right? Now, we're going to say that, again, the best estimator is, because we only look at one estimator, you can pass different estimators as well. Because we only pass one SVC, so not surprisingly, the best estimator is the SVC with these features, right? And I'm going to make a new variable, call it yhat optimized. And if I do grid.predict, because the model has been already trained, now I can call the predict method out of that, right? So I do predict, and I make predictions on the test set. Then I'm going to add this yhat optimized to the predictions which I already constructed up there. So remember, it has 2 columns, y and yhat. Now I'm adding the yhat optimized. Now let's look at the tail of the data. Look at that. It's already doing a better job than the blank SVC function, right? So this is the output of the SVC. This is the output of the optimized SVC. So as we can see, for this observation, y is 1. So both of them are making correct predictions, but this one, the optimized version, is doing a better job, right? So the actual y is yes, overload, but the SVC, the blank SVC, says that no overload, but the optimized version was able to correctly classify that observation, right? All right, then now I can look at the outputs, the optimized version, right? So actually, let's compare them. So this is what we got out of the blank SVC with the default inputs, right? Again, I'm not interested in accuracy, but let's look at that 97%. This is what I care. Can I improve this number? So 78%. So let's see if we can improve that number. So if I run this line, the accuracy is 97, but yes, this increased, right? And I'm not surprised, right? Because this is what the model went through in order to find the best combination. So the F1 score is 82%. This is really good. This is really good, especially if I compare it to the output from our homework, the KNN, which we use the same data set. So if you look at the answer key for the homework, if I scroll down, when the threshold is 50%, again, if I want to compare apples to apple, I don't care about the accuracy. This is high, but look at the F1 score. F1 score is 55% versus what we have here is 82%. So SVM is outperforming KNN by a large margin, right? Okay. All right. Then, yeah, we're almost done when in terms of training the model and testing it and using the grid search. Just be aware that this grid search is going to take a while. And you should, I don't know, Pat, you should be, if you want to make a guess, you make some educated guess, right? And gamma is usually in a scale of 1%, 1,000, 1 over 10,000, something like that. And C usually is in a scale of 1, 10, 100, 1,000, and etc. Right? We're going to play around with these things when it comes to visualization. That's going to be super fun. All right. Then what else? We can do cross-validation as well. Okay, let me ask you a question. Why do we use cross-validation? I already said that there are 2 reasons that we do cross-validations, right? Do you remember those? Yes, number 1, tuning hyperparameters. Number 2, estimating the performance metrics of the test set, right? Because we don't necessarily observe the test set. Not necessarily the test sets are always labeled. And more importantly, we don't want to cheat, okay? So in this case, we're not going to use cross-validation for tuning hyperparameters. We are using grid search cross-validation for tuning hyperparameters. So the only other application is to make some predictions, to estimate the performance metrics in the test set, right? So I can go ahead and say, actually, I don't want to estimate the accuracy because, guys, at the end of the day, here we're estimating the accuracy, this 97%, but I want to estimate the F1. So let me fix this one. And I'm going to push it to the repository because this data set is imbalanced and I don't necessarily care about the accuracy. I want to get an estimate for the F1. So let me call it F1. And here, why the cap is on. So let me call it F1 score to make sure that F1 score. And then I change the scoring to F1, right? And I make sure that I use the optimized value, optimized hyperparameters. So C is equal to 1000, gamma is equal to 1000th. And then I do the cross-validation. How many folds? 5 folds. So this is going to take a little time. Okay, now I can look at the F1 score. I have 5 of them because we're doing 5-fold cross-validation. And then I can report the F1. This F1, I call it F1C cross-validation. This F1 cross-validation is an estimation of this number, right? If I take the average, I get the estimated number. Yeah, thank you so much. F1 score. Yeah, so it's 82%, right? So yes, it's pretty much close, right? So it's an approximation of the test set, of the performance metric in the test set. So this is the number that I trust. And this is basically the number in this setup. This is the number that we care, not the accuracy necessarily. All right. So this is how we do SVM in Python. Is there any question about the steps? I'm going to go over the visualization. OK. So now let's do some advanced visualization. Again, this is not something that we do in real world. Just for learning purposes, we can do it here because we are going to stick into 2 dimensions. Oh, maybe you have a real world question on hand and it's only 2 dimensions. The feature space is only 2 dimensions. You can do that, right? You can literally visualize everything. But if you only have 2 features, the features better be not categorical because if it is categorical, then you cannot get a good decision boundary. It doesn't. I think we talked about it on the whiteboard the other day, right? All right, so let's say we have 3 continuous random variables. I'm going to work with temperature and wind speed, right? So from the scaled data set, I'm going to make a new data frame, call it data frame viz or visualization, whatever. And then I keep 3 variables. Overload, this is my target variable, temperature, and wind speed. Let's quickly look at the number of. We can normalize it and multiply by 100. Yeah, so it's 92%. You can round it up if you wish. It's 92%, 7.3%, right? So we have already seen this number, right? This is nothing new. But I want to show you a trick here that how can you make an imbalanced data set into balanced data set. And I'll talk about it, why sometimes it works, sometimes it doesn't. But there are 2 ways that we can make an imbalanced data set balanced, right? So the first one is that so look at the imbalanced data, how many observations you have, let's say 100, then shrink the size of the balanced part into the imbalanced one. Does that make sense? So basically, let's do it in practice. So the first way is to, how many overload is equal to 1 I have? So I want to see df viz. If I do location, I want to look at this data. Well, actually, I can copy this one. So these are the number of, in the data set. So this is my data set, right? I want to count how many of them are overload, right? So I can look at the shape. So it's 1,200 of them are overload, right? 1. And then, oh, I see. what I was doing. So the reason that I didn't put it here, because I wanted to look at the numbers. I forgot that. So here it's easier to do it this way. So we have 16,000, sorry, 16,000 non-overload and 1,200 overload, right? So this is highly imbalanced. So what can I do? I can say, keep these 1,279 and reduce these 16,100 to 1,279. Does that make sense? Work with a subsample of these guys. Another way is that, okay, how many non-overload you have? 16,100. Try to simulate these things, 1,200 up to 16,000, right? We are going to synthetically simulate data set, basically generating data out of these 1,200 observations. Does that make sense? Okay. So the second approach is going to, I personally I don't want to say don't like it, but it's not, it depends, it all goes back to the idea that if you torture the data, I will confess, right? I don't want to torture the data that much, right? So coming up with a synthesized data and then extrapolate it to a larger data set. So the second approach, I don't like it. But the first one, it depends. If I had 1 million observations here, I was way more confident to go ahead and shrink this 10 million to 1 million, because then I will end up with 2 million observations. That would be enough. Here, this only, out of, let's say 17,000 observations, only 1,200 of them are like this. So it's going to be very painful if I just delete, let's say, I don't know, let's say 15,000 of these observations, right? But just for training purposes, I'm going to show you how you can do that. But be aware that this is not a good strategy for this data set, right? If I had more observation, that was okay. But for this one, so usually in practice, people don't try to manipulate the data. You take the data as it is and then try to come up with better algorithm, machine learning algorithm, instead of playing around with the data itself.
Instead of switching it to like 50-50, would it be okay?
Oh, you can do
switch it to
60-40,
like
yeah.
80-20
Yeah, you can do that.
Okay.
Yeah. So
because in that case, then you wouldn't be removing too many observations.
that's also good, yeah. So Ryan is suggesting instead of doing 50-50, you can do 70-30, 80-20. Yeah, that's also possible. Okay. Well, actually, we can play around with the size here down, and you can say what's that. Okay. So how can we do that? So first of all, we're going to look at the location. Remember, we have lock and iLock, location, index location. If I do location, I'm simply filtering for the rows that the overload is equal to 1, right? And so these are, if I look at the head of the data set, these are going to be only the observations from the data set that the overload is equal to 1, right? We are going to import sample from random class. So this is a class from random. We're going to import sample. Let me actually import it once and show you what are we doing. So now the sample is imported. If I do sample, you have to pass a list, right? So if I pass a list of a bunch of numbers, 1, 2, 7, 8, let's say 10. You pass a list and say how many of, we're basically sampling from a distribution, well, it can be a distribution as well, right? We're sampling from a population, let's say, or we're subsampling from a sample. Let's say, give me a sample size of 3, right? So out of this list is going to give me 3 of them. Does that make sense to how the sample is working? Okay. Now, instead of this, usually we pass the data frame index, right? I can say df viz index. Well, let me remind you what is the index of df viz. So it's going to complain because it's not a list. We have to pass a list, right? So this is a list of my DF visualization of indices in the DF visualization, right? It starts from 0 to, really? Usually there's a cut in between. It didn't. Okay, to 1,000. Something is wrong here, but anyway, you get the idea. This is the index number, right? Okay, that was not the best way to show that, but anyways. Okay, so these are the index numbers from that visual. Usually we look at df.index, but here I want to do further, right? I want to say that, so I'm explaining what I'm doing here. from this data set, DF visualization, only select the ones that the overload was equal to 0, and then give me the index of those ones, and select 5 of them for me. So this is what this line is doing, right? Make a sample size 5. So these are the indices. And as you can see, if I just run it multiple times, I get different numbers, right? Because the sample, unless you wanted to set a random, I think there should be a sample should have a random. Oh, I don't see it here. But there must be ways that I can fix the random state. Okay. All right. So what I'm doing here says that I'm going to divide. I'm going to make 2 new, let's call it objects, right? Overload only and non-overloads only, right? So the overloads only are, I'm going to work with a sample size of 100 out of this DFViz data set when the overload is equal to 1, right? And then non-overload, again, the same 100 obs. Make sure that if you want to do 50-50, you call it 100-100. As Ryan said, if you want to do, I don't know, 70-30, you do 140-60, and etc. Right? So this is the place that you can play around with that, right? But here, for the sake of argument, because I want to do visualization, I want to basically make it 200 observation. I can literally look at all of those dots, right? Especially if I do a train test split of 20-80 or 30-70, 30 multiplied 200 is 60. I can visually see that 60 observations, right? And then I'm going to make them data frames, and I'm going to concatenate those data frames and look at them, right? So this is, I will replace my DF visualization to 200 observations, right? So the first 100 observations are the one when the overlap was 1. The second 100 observations are the one that the overlap is 0. So this is a method that you can basically make an imbalanced data set to balanced data set. Does that make sense? Yep.
You said in the code, you said that it was just the 100 that you put at the very end.
Yeah. Well, here, very good point. So in practice, I should have put the number, where is that? This one, 1279, right? Okay. If I want to do 50-50. Yeah, if I want to do 30-70, I can do 1200 and then maybe 1800 there. Okay. Yeah, and so basically at the end of the day, this is a balance. This is completely balanced data set, right? I have 100 ones and 100 zeros. Okay, now let's do visualization for that. So we're going to define our x and y, the target variable. What's the time? Okay, very good. X and y variable like this. So x is going to be 2-dimension, temperature, wind speed, and y is overload. Let's make a train test split by 20-80%. So my test set is going to have 40 observations, right? 20% of that 200 observations, so it's 40 observations. And I'm going to scale them. Then let's start with the very basic one, the default inputs. C is equal to 1, kernel is equal to RBF. And let's look at the plot. We don't need this index. All right. So this is our decision boundaries using the SVM classifier with the default values, right? So I think if I do it one more time, I get different numbers, right? I get different shapes. So let me, yeah. All right, you get a different one. But the point is that these two, so this is the train set. So the model is learned by, as you can see, it's using RBF, and gamma is the default by now. Right now it's a scale, but we're going to play around with those hyperparameters. So this features, this shaded areas are going to be completely defined by going over the train set, right? Then it means that if I go over the test set, well, the scale is different. So if you want to see exactly the same thing, so what do we have? 3 minus 3, 2.5, 2.5. So I think here, I just want to make sure that this is exactly the same. The shaded areas are exactly the same as here in the test set. The reason that you see them somehow different is that because the scale is different. So let me manually fix them. So we have minus 2.5, 4.5-ish. So let's do that. Y, yeah. Minus, what's that? Oh, This is my y variable, right? So if I do minus 2.5 and 4, am I doing it wrong? I think this should work, right? I want to change this scale from minus 2.5 to 4. Make sure that you'll see this exact same thing, right?
But I don't think you actually ran that code yet.
Okay. Oh, you're right, I didn't. Okay, so I just want to show you that how we can manually do it. Yeah, originally it was the same, but well, not the same. Well, for something, they must be the same. So sorry, I'm a little. Let me change this one to 3.5. Yeah, because in the test that there is no observation here, so it doesn't plot anything. But you get the idea. You should complete that part. Okay. All right. So this one, we have 18 misclassifications out of 60, which is, well, something. Well, we care more about the F1 score, right? So I have to count the precision and recall and then do a harmonic mean, right? So now let's play around with this, right? So let's go ahead and change the kernel to linear and polynomial, right? Yeah, we do have time. We can look at all the combinations. So let me go ahead and change the kernel to linear. Before running this, before looking at the output, how do you think it's going to look like? The boundary is going to be a line, right? So it's not going to be that curved shape. So this, yeah, this is like decision tree here. It seems that so in this, so what does it tell you? By looking at this linear kernel, well, I wish we have studied the decision trees, but we haven't yet. But this is interesting. What does this suggest to you? If you want to tell me that temperature is more important or wind speed, if I show you this classifier at the end of the day, which one is more important? Temperature, right? So it seems that the algorithm doesn't care to wind speed at all. Actually, the weight is literally 0. Okay. Well, yeah, maybe there's a little tilted, but that's. Okay. When I was running this code at home, this didn't happen, so it's kind of unexpected. But anyways, yeah, then you can run the same thing for the test set. Yeah, and let's look at the number of misclassifications. Well, it slightly improved, right? 14. You see, the linear one, the simple linear one, at least in this example, in the test, it is outperforming the RBF, which is surprising, right? So let's play around with other ones. So we have linear, polynomial. If I do poly, not surprisingly, it should be a curve. Yeah, see, because I have quadratic version of temperature. I'm adding quadratic version of wind speed, and who knows? Oh, by default, it's the degree was 3, right? So I'm adding quadratic and cube and all the interactions. Interaction between degree 1, 2, 1, 3, 2, 3, and etc. Right? So this is how it's going to look like. What else do we have? Well, let's actually be complete and show the outputs too. Yeah. Again, these are exactly the same. Just if you see them a little shifted because of the scaling. If you make sure that the scaling is the same, it must be because the model is trained on the train set. Well, this is really good actually. Well, if your goal was to minimize the false negatives, maybe polynomial was your answer. Okay, because here in SVM you cannot play around with the threshold, but maybe at the end of the day you can play around with the confusion matrix and see which one is giving you what you want. Right? And then let's do different Cs, right? So let me go ahead and actually change this one to RBF and increase the C, the cost to, I don't know, 10,000. What do you expect to see without running the code? So if I increase the C to 10,000, am I overfitting, underfitting? What's the answer? You're overfitting, right? Because C is very large, means that the margins are going to be very small. So it's going to be lots of errors, and we are overfitting, right? So let's look at the output. There you go. It's completely overfitting. And I don't know why this happened, right? Because in the train set, there's nothing here. This is interesting. But obviously, this is overfitting, right? And now if I apply it to the test set, it should do a poor job, right? Well, no, not yet. 12, 19, yeah, it's the worst compared to the other ones, right? So it's completely overfitting because this is, I don't know. Surprisingly today, this is not cooperating with me, right? Even in the test set, it's not that bad. Anyways, you get the idea. So if I go ahead and change the C to, instead of 10,000 to a very small number, you cannot literally pass 0. If you do 0, it's going to complain. So if you want to make sure that it's very close to 0, you can do something like this, right? So if C is very, very small, basically you're basically telling the model that we don't care about the misclassifications. So what will happen? Then the margin is going to become wide, and then it's going to get close to linear somehow, right? Does everyone agree with that? Guys, remember, if we talked about it here, if C is equal to 0, literally 0, do you remember that at the end of the day, your classifier should be linear, one line? Okay, so this is what, and let's look at that. Did I run it? Yeah. Oh, am I doing it correctly? Yeah. Something is smelly here. This should become, I don't know, maybe this is not a, it should be a lot more smooth than this, because 1 and 1,000, 1 over 10,000 is roughly the same. That doesn't necessarily make sense to me. Maybe there is some boundary order, but I'm not aware. Yeah, it should become a lot more linear than that. I don't know. Something is going on here. It shouldn't be like this, or I'm missing something. All right. Let me just try one more number. Or if it is, that's because of the gamma, maybe, because gamma is a scale. So let's change the combination. Yeah, because
I would argue that is closer to linear than what we previously had.
It should be. Well, yeah, it is, but it should be a lot more smoother than this, because I literally put C is equal to 0. But anyways, well, I trust what I see here, right? So not what I think, because the data is telling me that this is how the classifier is going to look like. So let me go ahead and add gamma, and we stop here. So let's do gamma. What combination we can think of? Let's do C is equal to 1, gamma 1% 10. C is equal to, I'm going to play around with small c and different gammas and see what's happening. So if gamma is small, very small, what do you expect? So if gamma is very small, so again, it should be closer to linear, more smooth, right? I hope that it cooperates this time. It should be. There you go. Yeah, it's super sensitive to gamma. Yeah, I was expecting for C to do the same thing, but it seems that because the default gamma is 1 over scale and the size is a scale and the size is very small, so we get a large gamma by default. Are you following what I'm saying? Yeah. So that was what's going on, because this train set was super small. 1 divided by variance of that small number is going to be a large number. So it's already the gamma was large. So that's why I didn't get this linearity, right? If you do with larger data set, if your data set is large and you make sure that your C is small enough, let's say 100, 1 over 10,000, you should get something linear, as exactly what we were seeing here. The reason that it didn't happen because our data set was super small. And we were using the default gamma, and the default gamma is inversely related to the variance of X. Does that make sense? All right, I'm glad that I found an answer to my mysterious question myself. All right, and then for the test set, and then lastly, let's play a large gamma. If I do gamma is equal to 10, so what should I expect to get? look at that. If gamma is large, and then yeah, we're overfitting, and it's going to be lots of these circles because these are different, what do we call it? Landmarks, right? So we're putting a bunch of landmarks in the data set, and then basically you have lots of those hump shapes around it in 3 dimensions, right? So let's look at, let's do gamma is equal to 10. I can even increase that gamma. Let's play around with that.
Is there a threshold on how high you can go?
No, I don't think so. Yeah. I don't think so. Well, you see, this is absolutely overfitting, right? So according to Ryan is asking, can, I don't know, 1 million maybe? There's no, because it didn't complain already, right?
Yeah.
Usually if it is 0 and you, oh, look at that. Right? So what does it mean? It means that the majority of the data, well, it was 50-50. We defined it to be 50-50, but it's saying it, so it's picking it randomly. Are you following? Because it's literally counting the number of reds versus green and then classify them like that. But yeah, but it seems that it's picking it randomly here because it was exactly 50-50. All right, so let's put it back to 100 and then call it a day. Okay, it's absolutely overfitting, right? So this is ridiculous. So these dots, these green shaded areas. Let's look at the test set. Yeah, see these weird green shaded areas. It's not going to work for the test set, and this is the worst case, right? No, if out of nowhere we call this area green, and we were so unlucky that they had 2 observations in the test set, the red observation in the test set right there, right? Yeah. Look at this one. Yeah, this one. Well, this one is good. Okay, it's like a duck with a beak. I don't know. Okay, I hope that you had fun with this visualization. That helps you understand what basically do these hyperparameter tuning do. But usually, when you work with more data sets, when you become more experienced, you will see that there's a threshold that you get. So for example, you get an accuracy of 95, you get a F1 score of, well, 95 is exceptional, right? But in general, whatever number you get, right? If you run the default version of the model, let's say you get an accuracy of 70%. And then if you do hyperparameter tuning, if you tune the hyperparameters, you can go from 70%, let's say, to 75. You cannot make a miracle, you know. There's a cost, you know. You make the model more flexible, and then maybe 70 go to 72, 74. So you cannot go from 70 to 90%, right? Usually you will stop searching around and say that if I don't get a good accuracy with let's say with default values of the SVM, and I play around with it a little bit, but it is what it is at the end of the day. You have to change your algorithm entirely. So if it's not working with the SVM, you have to do random forest. You have to do some other methods, right? All right. I think that's pretty much it. So is there any questions? Let me see what else do I have. I put a bunch of links here. So if you're interested in the background of how these things is the convex optimization, these are relatively easy reads, except this one. This is a book. This is an entire book. But again, for those of you who are planning to do a PhD, convex optimization is going to be, I think, your day-to-day kind of thing that you play around with. ROC multiple class. Oh, this is for multiple class SVM in Python. You can look at that one as well. And so for this is from toward data science. Let's see. So for example, we have 3 classes, and then if we change that, OVR or OVO is going to do the job for us, right? If you have multiple classes. And grid search, cross-validation documentation, decision boundary visualization, and I think, Sarah, you asked a question how we can do these things in Python. So I think this is a link. Yeah, you can borrow some other people's codes how to do decision boundaries. All right. it's 4:11. Let's call it a day. And next class, I'm gonna do support vector machine. Oh, did we compare these two? This one with KNN? We already did, right? Or we didn't? We did. We did, I guess. Yeah, we compared with KNN. Yeah. I think we did.
There's a lecture, like the PDF lecture.
Yeah. Well, let's see. Yeah, we compared it. With, yeah, we did compare. So it's 55% versus. What was the number here? We got a very large number up there.
It was 82%.
Yeah, 80 something percent. Okay, good, good. So let me stop the recording.